Again, welcome back to Past Engineering. No intro needed. Let's get back to chemistry once again. And we're doing the chemistry. Okay, right over here. This way. And there are the two types of free energy. What is the free energy? And the thermodynamics. The second of thermodynamics introduce the concept of entropy. And the feasibility of the thermodynamics, that means feasibility of the mechanical work cannot be described in only one randomness and in only another is a free energy. So it describes there are the two types of free energy. One is the Helmholtz free energy. There are the two types of free energy. Two types of free energy, and one is the Helmholtz free energy, another is the Gibbs free energy. One is Helmholtz free energy, another is the Gibbs free energy. These two terms are important terms in the chemical thermodynamics. In the chemical thermodynamics, so what is the Helmholtz free energy? Let's discuss about this Helmholtz free energy and the Helmholtz free energy definition. Definition of the Helmholtz free energy state that the maximum amount of energy available isothermally to a system that can be converted into useful work is known as is known as Hellman, is known as Oak function, is personally known as the Oak function. Oak function are the Hellman's Oak function are the Hellman's function. Oak function is the Hellman's function, and it is denoted by A, and it is denoted by A, it is denoted by A, and it is extensive property, and you know that extensive property means that depend upon the amount of substances present right over there. And let's go to simple calculation and mathematically, and here is the formula of the Helmholtz function, and the mathematically the A equals to u minus t into s, where is the u equals to, where is the u is denoted as the internal energy, where u is denoted as the internal energy, and the t is the temperature at which the experiment is going on. That means the temperature in the Kelvin scale, and the S means the entropy of the system. That system of the certain amount of entropy. S with the entropy in the system. That means the entropy. The randomness. That Ts with the loss part. That is the U minus Ts with the loss part, and the U minus Ts is the effective work. This is the effective work. And let's discuss about the Physical significance. Physical significance of this. Physical significance of the hormones are the work function, and the isothermal. Let us consider the system is going to. Let us consider and the isothermal process involving the change from one to two state. Then relation can be obtained as then A1 equals to U1 S1, and isothermal process the temperature is constant A2 U2 minus S2, and the A2 minus A2 A2 and this is 2 minus the H1, and it is V2 minus V1, and this one is the. Okay, this is the final, and the final is the change in Oak function, or effective Helmholtz function equals to del U minus del Ts. This is change in entropy, and internal energy. That means the del U equals change in internal energy. Change in internal energy equals to del A plus del A plus the T del S. This is the important thing you need to understand. Okay, let's move to next slide. Okay, here, and that del equals to del U minus del Ts, and the T equals to q by t, and the del T equals to q by t. We know that the entropy, so that the del A, that Helmholtz function equals to internal energy, change in internal energy minus the Helmholtz function equals to change in internal energy minus the energy. That means the quantity of heat or the amount of substances present. And from this again, again from the first law of thermodynamics, we state that Q equals to del U plus P del V, and the Q equals to del U plus the work function, that is the work done. This is one is the effective work done, and so internal energy equals to in Q minus del U, and from this call this will come here. And if you substitute the internal energy right over here in this equation, and we got this, we get, and if if you do the simple substitution, over here, and this one is the simple substitution. If you do the simple substitution, and we get this del equals to q minus del t, and the del a equals to negative of q, and work done equals to negative of del a. This can be written. That means this means okay, this means the work done equals effective work equals to Hellman's function equals to negative of the effective work. This one is true. And let's move and this define the what is Gibbs free energy G, which is denoted by the Gibbs free energy, which is denoted by the G. That means the Gibbs free energy. And here this one is the Gibbs free energy. Gibbs free energy denoted by G is the maximum, and this is the same definition. Let's go through it. It is the maximum amount of energy isothermally. That means point to be noted isothermally available to system that can be converted into useful work. That can be converted to useful work, and it is represented by G. And it is extensive property right over here. It is extensive property, and mathematically we come to know that G equals to S minus del T. G equals to S minus del T. Son, oh son, G equals to S minus Tc, and in the Helmholtz function we come to know that A equals to U minus Ts, and here is the G equals to S minus Ts. S minus Ts, where is the G equals to Gibbs free energy, S equals to enthalpy. The enthalpy as is denoted by the enthalpy, that is also the energy, which is the sum of the work done at the constant pressure, which is the sum of the work done at the constant pressure plus the internal energy, minus T with the temperature at which the process is carried out. Ts with the Ts, and the Ts with the amount of energy or disorderness lost by the system or the process at temperature T. And this T minus S, the T minus T and S minus T is the amount of energy isothermally available for the effective work. Let's discuss about some physical significance. That means the two conditions. One is the initial condition right over here, and here is the initial condition, and this one is the final condition. Okay, and this one is the G, and this one is one formula for the G of the initial condition, and this one is another important formula for the G in the final condition. Okay, so if you subtract the final function with the del G equals G2 minus G1, if you know, if you do simple calculus right over here, and we come to know that the del G equals to, come to know that the del G equals to this one, del S minus del S minus the T del S, T minus del T S, and from the simple calculation, this one is the from the del S equal to del U plus del S equals to del U plus P del V. First of thermodynamics, in terms of enthalpy. Enthalpy is the sum of the change in internal energy plus the work done at a constant pressure, not a constant volume. So del G equals to, and using that and putting that equation, del G equals del U plus P del V minus the del T S, del G plus del U plus minus del T S plus P del V. Actually, we will P del plus P del V, and del G equals to, and del U minus del Ds. Del U minus del Ds equals to Hellman's energy A plus P del V, and we come to know that, and here is the another, and the one the biggest formula right over here, and this gives the Hellman's function del equals to U del U minus del T minus T del S. Hellman's function, this one is the, and so it comes to know that this equals to the relation between the Hellman's function and the Gibbs free energy. Gibbs free energy, change in the Gibbs free energy equals to change in the Hellman's function plus the P del V, and from is we know that the del equals to negative, and multiplying the both sides by the negative del G, and the negative of the work done equal negative of the Hellman's function equals to, and del A del G, and the minus of P del V. This one is the another important formula you need to understand right over here. Important formula you need to understand, that means the negative of the Gibbs free energy equals to work done minus P del V. negative of the Gibbs free energy equals to work done minus the P del B. Okay, this one is the one of the important formula. Use this. So here and so here we come as a conclusion. So here we come as a conclusion, and this one is the important formula we derived, and this one is also another important formula we derived. This is another we derived, and here we come. Here is our conclusion that therefore decrease in the free energy is the maximum work obtained from the system. That means decrease in the free energy. That means del G equals maximum work obtained from the system, and system other 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 than that, due to change in volume, that is the network. That means the maximum work, that means decrease in the free energy del G, decrease in the free energy, that means this del G, that this decrease in the free energy, this del G equals to is equals to maximum work obtained from the system other than excluding the other than that of a change in volume, that is the network. This one is the one of the important formula and gives free energy in chemical thermodynamics. Okay, hope you guys understand the video right over here, and this is the short video for you. So this one take a lot of advantage and will be excellent. Okay, thank you.